Hello CIO class, and welcome to yet another installment of Chemical Engineering. In this lecture we will be going over other types of flow that you can get. So we've done Newtonian flow, etc., and now we're going to go into other types. We will briefly go over how to deal with things like non-isothermal flows before moving on to the effects that certain fluid movers can have on the flow rate, as well as the pressure due to the pulsations that occur, and also ways that we can deal with changes in or fluctuations in these pulsating flows in our design and operation of piping systems. This includes the use of correlation factors to or safety factors to account for a periodic fluctuation, and also how to dampen such fluctuations, because sometimes you can't change the fluid mover, you'll just have to try and dissipate fluctuations. Now, non-isothermal flow is obviously going to be a temperature change. So isothermal flows can be achieved through good insulation if you think that you're going to have a non-ideal case. But even so, temperatures may change due to other factors, and this change obviously needs to be accounted for. A gradual change in temperature increase across, so let's say you have a temperature increase or decrease, it can occur even if insulation is present, because maybe the insulation is not effective. Alright, but a gradual temperature change can also come about due to inherent changes that happen in the process that aren't completely necessary. So, for example, in the case of a heat exchanger, so inside the tubes of a shell and tube heat exchanger, you would of course want to have a change in temperature, because that's the point of a heat exchanger. So how do we deal with this? Stepwise or sudden increases in temperature occur where flows are entering a heat exchanger for the first time, or into a reactor. Maybe it's a CSTR reactor, etc. And this can result in sudden changes in the temperature. It could be at pipe entrances, it could be at pipe exits. Okay, so it doesn't matter. But for gradual changes in temperature, a correlation factor, which is shown here, is used with the Darcy-Weisbach equation. Now, this correlation factor uses the ratio of viscosity for the fluid at the wall and the viscosity of the bulk fluid inside the pipe away from the wall. And the exponential m is chosen based on the type of flow regime that you would expect. So these are in the handbook, so if you do forget them, but you kind of remembered, oh, there was something like this in the handbook, just have a look in this chapter. You'll see that this information is specified. These values are there for you. Now, fortunately for you guys, all other pressure differences can be evaluated as for isothermal flows. Okay, so we take the non-isothermal case into account using the Darcy-Weisbach equation, just like we do frictional losses. Now, in most cases, density differences are treated as negligible, but remember to base all density calculations on the upstream density and perform the necessary checks. Alright, so always check, don't assume. Remember, design, you cannot just make an assumption. Your assumption must hold true. So, for example, recently I sent in a paper for publication, and I made a list of assumptions, and later in the paper I validate the assumptions with data. I show that my assumption was reasonable. Alright, and assumptions aren't simplifications, they are evaluations on the process that are correct. So if your assumption doesn't hold, it's not correct, then obviously you can't use it. So always remember to do your checks. Do the checks and the balances. Okay. Now, for stepwise changes in temperature, calculations are performed in the case of isothermal flows. Okay, so with the exception of, as I said before, delta PF prime, and also elevation pressure drops. Just note the pressure drops that I have listed here and which ones are not accounted for. Okay, so for non-isothermal flows through the heat exchange equipment, we follow procedures outlined in the heat exchange section of this module. Okay, so the heat exchange section, all about heat exchangers, that is a separate module altogether, so we will be discussing that and have a look at pressure drops. Now for both friction and elevation, we calculate the pressure drop stepwise, and because it's an energy balance, remember we're talking about a mechanical energy balance, it's summative. So when we do the calculation for the pressure drop stepwise, we can sum up the individual terms. Okay, so that is what I'm showing here. Now another type of dynamic that we need to take into account or be aware of. So in industry you'll see there are different fluid movers for different applications, and if you have to do a design or your boss tells you to evaluate a pump, or maybe they've lost the pump curve and you have to now do pressure tests, just remember that there are different fluid movers, and we will get to fluid movers in chapter 11 of the handbook. So we have to account for the effect that fluid movers have on the flow, and this effect is called pulsating flow. Okay, that is caused by the reciprocating motion, the back and forth motion of fluid movers, such as piston pumps. So specific fluid movers will cause this type of reciprocating action. So piston pumps, syringe pumps, and crankshafts. Okay, it's based on the type of mechanism that they use. These pumps are very necessary because they can reach massive pressure differentials. So if you're looking for very high pressures, these are the pumps that you would typically choose. Compressors can also do it. They're just very energy intensive, right? So pumps can be quite energy intensive, and this needs to be kept in mind. Now the cause of the dynamics are obviously due to the velocity becoming zero at certain intervals of the stroke action. So watch the stroke action and think to yourself where the velocity is going to equal zero. Okay, so I've shown it here at the purple points. Just look at the purple circles and then look what happens at the piston. The piston stops and has to reverse, and then it goes and it stops and it reverses. Okay, so this is the cause of these dynamics. Now at certain positions of the piston shown here, the piston stops moving while it changes the direction, as I've said, and in doing so it halts the motion of the fluid also periodically. I mean, think if this is incompressible fluid, it's not going to move much, if at all. Okay, so this causes pulsation. Okay, so this pulse, okay, it needs to be accounted for when you're designing piping systems, if you're designing with these sorts of pumps in mind, so that abnormal or unsafe operation conditions can be prevented. What do I mean by that? Well, for pipes you have a certain pressure limit. Okay, so if you have an average flow rate, that doesn't say that you're operating at that average flow rate. With process dynamics, you will understand that there are definitely going to be disturbances in the process. You know, my time in industry, when I was working at the plants, you know, we had various mills spread across the country, and I had to visit all of them. And um, one of them, for example, was operating at 19% of its design efficiency. In other words, 19% of the time it was hitting the set point. The rest of the time it was fluctuating over the set point and under the set point. And so we need to account for these abnormal operations. They can come from the pump, but they can also come from changes in heights of the level, or the process controller changed set point upstream and it has a ripple effect downstream. Okay. Now, change in the velocity can be described using the following equation, which you have probably seen before in physics and also in COP, where USM is referring to the momentary velocity of the piston or cylinder, which is responsible for the pulses. Now again, if you don't understand something, or maybe I've mixed my words and said something that doesn't make sense, always remember to go to the handbook and just verify what I'm saying, because maybe I make a mistake. Alright, now omega is obviously referring to the angular momentum, okay, in this case, and its product with the radius gives the term of revolutions. So together it's radians per second. Well, omega t is the angle of rotation. Okay. Obviously depending on time, in which time position you're at. When the radius is at its maximum, as measured from the plane of action, which I give you as a dotted line, the maximum velocity is obviously going to be obtained, while the velocity is going to reach zero when the radius of action is aligned to that plane of action, okay, that dotted line. So when everything lines up on the dotted line, zero. And obviously on the other side as well, so you have two places where you're going to have a zero velocity. Okay, big problem, because you want flow, and now you stop the flow, you stop the flow, you stop the flow, and you have a maximum. So obviously the average velocity that the fluid is going to flow due to this reciprocating motion is going to be based on these two stop positions and one maximum position, where if the fluid, for example, is incompressible, we need to obviously then adjust for these inefficiencies in the momentum transfer from the piston to the fluid using an efficiency term, nu, as shown here. Nu we usually use for efficiencies. This equation describes the flow on a volumetric basis and is used to account for differences between the volume of fluid inside the piston and the volume of fluid that's actually being pushed through the pipe. And these two things can be slightly different. So I mean, this term can be like 99.9%. It depends on the efficiency of the piston that, you know, that has to do the work. Sometimes the fluid mover that you're working with is 82% efficient, like a centrifugal pump, or 85%. Okay, of course, not all the volume of the fluid inside the piston is going to be transferred into the pipe in the case of a compressible fluid due to the performance of the fluid mover in question, etc. So compressible flows, think about how they would react to this stop and start motion. Obviously a bit better. They have a bit of a dampening effect because they can be compressed. But nu is going to be much lower, because by the time your piston is to the far right and it's pushing, it's pressurized fluid, and the pressure is now alleviating before the piston then moves backwards. Alright, so there's a bit of an inefficiency going on here. Now the question is, how do we incorporate this velocity into mass flow rates? Okay, because obviously we want to do a mass balance. We use this equation. We simply substitute it as shown here. Okay, so mass flow rate is equal to rho UA, or rho V, where capital V is the volumetric flow rate in units of like meter cube or liters per minute, per hour, per day, per annum, etc. Now, what about crankshafts, where you have kind of a pseudo continuous rotation instead? Okay, so it seems like there's this continuous rotation, but there actually is kind of a pulsation that's caused by the pistons. Does delta PF prime vary in this case? Well, yes, of course it will, but obviously to a much lesser extent compared to a single or double acting piston. We'll talk about these different pistons, the single and double acting. But we do not need to include all the variations in pressure. We just apply some average value to account for these changes to the flow rate. Okay, so but before we get into this, let's just consider what happens in the case of compressible flows. So for compressible flows, like I've said before, there's some dampening effects that take place, and we perform pressure losses as if there was no pulsation or no pulsating flow. However, we still need to apply a safety factor in piping design. Why? Because we don't want our pipes to burst and kill populations, like what happened in Bhopal, for example. There was a loss of control, there was too high temperatures that were reached, and the pesticide left the tank in the middle of a populated city, immediately killing I think 3,000 people as they slept in their beds. So very important safety factors. 1.3 for compressible flow, and this is to make sure that design is operational. And what I mean by operational is that it will not break, it won't kill anyone, which is actually not a laughing matter, so keep this in mind. In the case of liquids, which we obviously treat as incompressible, a pulsating factor is incorporated as shown here. Normally this safety factor lies between a value of around 1.2 or higher, but it all depends on the type of fluid mover in question. So let's look at some common variations that are employed in industry. Okay, so this pulsating factor is a complex factor that you can determine by hand, but 1.2 is an approximation that works. It's safe enough. It accounts for most of the maximum flow rates that you will hit. Alright. Now, what sort of pulsating actions are we talking about? So what sort of fluid movers? Well, the first one that we looked at was a single acting piston. Okay, the one that I showed before to start this explanation. The second one is a double acting piston pump, which is shown here. Okay, it's an ancient Chinese invention that was used to drive the furnaces, and it lessens the break period in flow, reduced only slightly, so there's less stationary motion. Okay, but the double action is nice because as you pull back and pull forth and pull back and pull forth, you'll always more or less have a flow out. Okay, and you can compare this with other ones. So in one stroke, compare this. How much liquid or gas can be delivered, per one cycle. So how much volume per stroke? Okay, So in one stroke you can deliver 2 volumes, whereas a single acting piston pump, one stroke you can deliver 1 volume. So this is obviously going to be slightly better, but obviously the pulsating action is still there. So just have a look here. Right, now these 3 cases that we've spoken about have their own safety factors, FP, obviously. The delta P F prime is determined as before. Okay, Darcy-Weisbach applies, and the safety factor is used for each of the fluid mover. And you know, apart from the design factors used, it is also possible to include the addition of a dampener, okay, to dampen out the effects of pulsation. So, for example, you can include a gas chamber that contains a compressible fluid, such as air. If this is methane, then air is not a good idea. Air plus methane plus compression means big bang. So you would probably use CO2 instead, if this was liquid methane. But I think if it was liquid methane, you'd probably also liquefy CO2, so you'd have to think of another thing that you could do. Generally, in industry, we like to pump liquids. It's cheaper. Volumetrically, you can pump more in the same diameter of pipe, and it's better in terms of storage and handling. Okay, but in some cases, like with hydrogen, you're not going to want to pressurize it to liquefy it, because that pressure is just going to be ridiculous. I think it's like 700 bar. Can you picture that? Okay, so that is quite crazy. Now, in this case, the safety factor that would be required for these designs, these piston pumps, double acting and single acting, reduces slightly as shown to the following values. And all this information is available in the textbook, so you don't have to learn it by heart. It's also available in handbooks like Perry's Chemical Engineering Handbook, you know, for us chemical engineers. If you forget, if you kind of remember but you've lost your handbook for piping systems, these factors are available. Sometimes they come available with the pump. The designers of the pumps tell you these sorts of figures as well. Alright, and with that we conclude this part of the lecture. See you all next time.